All right, good morning, everyone. Welcome back to Physical Geology 1403. Let me turn off these lights at the front. How we doing? Did we have a good weekend? Yeah? Anyone looking forward to the Super Bowl? Yes? That was pretty emphatic. Are we a Seahawks fan or a Patriots fan? Seahawks, woo! Any Patriots fans in the house? I promise there won't be any repercussions if you are. I spent my whole life up until I was 19 being a Patriots fan because we used to live in Boston. And then I went and I lived in Seattle for a few years and then left there, but I ended up marrying a Seattle girl. So we are naturally Seahawks fans now. So we are quite excited for the Super Bowl. It's funny because I didn't hardly pay any attention at all to the NFL season until the Seahawks were going to the Super Bowl. And now we're all like, whoa, let's watch it. We're going to get food and friends and make a whole thing out of it. That's fun. I would wager that's probably most passive football fans. All right, I'm definitely not an active football fan. Okay, what else? Anything interesting? Anything that you want to talk about? Anything you saw in the news? Anything that happened? Anything that's going to happen? No? Have you heard about the Artemis 2 launch coming up? Well, why didn't you bring it up, bro? So what? I want to go see it too. I can't, but I would love to. So on Sunday, actually, is when Artemis 2 is launching. It is the most powerful rocket that humanity has ever built. Its mission is to take men further away from Earth than we've ever gone before. We are going past the moon. I say we royally. These astronauts are going past the moon, U-turning, and then coming back. So it's going to be pretty cool, pretty exciting. And it's kind of a demonstration of this rocket for that purpose. This is the rocket that will take people out into space. This is kind of more or less its last test. We've tested it before in unmanned or short missions up into space and back. This is the furthest it will ever have gone. If it goes past the moon's orbit, flips around and comes back with people on it, it's kind of the last test. As with most things, medical tests, technology tests, car tests, you always have to test it with a person in it. That's the last test. And once it passes that, you can use it for widespread purpose. So that's where we are now. It's exciting. Because then after that, we make more of them. And more of them, and then we can have a whole fleet of these things that are constantly going up to space and back. That's really exciting for someone like me who is working on making the policy to dictate things that happen out there. Because now we're actually looking at people going out there more consistently. Very cool. All right, anything else? Ivan, you don't have anything else that you're too shy to bring up? Not in particular? Okay. Week 4. That's where we are now. You are getting lecture 6 today. You're getting lecture 7 on Wednesday. Because of the amount of time that we have lost, due to circumstances outside of everyone's control, we do have to make up some time. So on Wednesday, you're getting lecture 7, and then we're having our exam 1 review. Normally, I would just give you lecture 7, and then prepare over the weekend for our review on Monday, and then give you 2 days to take the exam, and then pick up with module 2 on Wednesday, after everyone has taken it. However, due to the unforeseen circumstances of this term, we are going to need to have our lecture 7 on Wednesday, followed immediately by our exam 1 review. And then the bright side of that is instead of just having Monday and Tuesday to take the exam 1, like you would normally, you get Thursday, Friday, Saturday, and Sunday to take it. So you get twice the amount of time to take the exam, but less time to prepare for it, unfortunately. Within the classroom, obviously, you can wait to take the exam until Sunday. Totally fine. Prepare for those 3 days beforehand. Just don't, procrastinate it. Don't spend those 3 days not preparing and then take it when you could have had that extra time. You could have used that extra time. Okay, so think of this as a blessing more than anything. Okay, any questions about that? Okay, so just to make sure everyone's on the same page, this goes for my in-person class. My online class, this is going to be similar for you, but I'm going to send you a message with specific details for what's for you. You're going to take the exam either Wednesday after class, Thursday, Friday, Saturday, or Sunday. So technically you have like 4.5 days to take it, as long as it's done before you come to class on Monday. Okay? Cool. Is that a question, or are you just scratching your head? All right, cool. All right, well then, should we begin on today's content? Great. So we learned about weathering and erosion last time. Refresh my memory. What is weathering? The breaking apart of material. Excellent. By the way, you want to hear something tragic? Our last lecture, when I taught you about weathering, I had my microphone on. I had this on. I could see that it was picking up my audio, but the other end of this cord was not plugged into the computer. So I recorded that whole thing, and I couldn't use it. I had to record myself giving the same lecture again the next day for my online students. Made me sad. I mean, I would have had a lecture anyway, but I uploaded a lecture to my students without audio for 24 hours before I realized. Anyways, yes, the weathering, the breakdown of material. Thank you. There are two types of weathering, right? What are they? Chemical and mechanical. Thank you. What is erosion? The transportation of the material that's been weathered. Okay, excellent. Okay, so that's where we're at. We have broken down material that has been transported, and then it stops being transported. We call that deposition. What we have is called sediment. Have you heard that term before? Sediment? Sediment is weathered, usually mechanically weathered material. Okay. So now today we're talking about sedimentary rocks. Can anyone guess what sedimentary rocks are made out of? Sediment. Well done. Excellent deduction skills. Okay. Now sedimentary rocks make up about 70% of all the material here at the surface, but is still the minority of all the material our crust is made out of. Our crust is 90% igneous and metamorphic, but 70% of the surface is sedimentary. Why? Why is so little of the total volume of our crust sedimentary, but so much of what we have here at the surface sedimentary? Thank you. The processes that cause weathering and erosion only occur here on the surface. We don't get weathering and erosion 4 kilometers underground, right? It happens here, so this is where that sedimentary rock is, and it gets piled on top of that igneous and metamorphic stuff that makes the rest of the crust. Good. I'm glad that that logic made sense to you. Thank you. Now, sedimentary rocks are cool for a number of reasons. You learned about igneous rocks. Okay, you learn how to interpret igneous rocks to learn a little bit more about the environment, the cooling environment, the chemistry of the magma it came from. So they're cool for that reason. You'll learn about how cool metamorphic rocks are in our next lecture, but sedimentary rocks are cool because they preserve a lot of environmental factors within themselves, okay? Surficial processes, so the back and forth wave motion, the direction that a river is traveling, or wind. Even things that lived and then died can get preserved in sedimentary rock. You don't find any of that stuff in any other kind of rock. Only sedimentary rock can preserve those things. Okay? Talk about that more in a little bit. But also resources. Oil. The vast majority of all oil, natural gas, water will come out of sedimentary rock. There are a few exceptions. In Vietnam, there's an oil field where they get oil out of granite, not because the oil formed in the granite. I'll talk about how oil forms in a bit, but because the oil formed somewhere else in sedimentary rock and then got pushed through the ground system, through all the pore spaces in rock, and ended up filling in this whole igneous, cracked, shattered, broken igneous granite complex in Vietnam. So it's a really weird circumstance where you're pulling oil out of granite, but that is super not normal, okay? Oil, for the most part, comes from sedimentary rock, all right? So, and many other resources, not just oil or water, a lot of the other resources we mine do come from sedimentary rock. So what do we have? We have weathering. Our material breaks down. Whatever that material was, be it igneous, metamorphic, or sedimentary to begin with, it weathers down, becomes sediment. That sediment goes through either transportation, either through mass wasting or erosion. It gets transported somewhere. Eventually, it stops getting transported. Once it stops being transported and sits still, we call that deposition. After deposition, other things happen to it. There's a lot of other things that can happen to it. We kind of take all that stuff that happens to sediment after it is deposited and call anything that happens to it diagenesis. I'll talk more about diagenesis here a little bit later today. But diagenesis is the word we use to describe anything that happens to that sediment after it is deposited. Okay? So that's our kind of sedimentary process right here as part of the rock cycle that we've discussed. So, now let's talk about the different types of sedimentary rock. We can take sedimentary rock and group them into two broad categories, clastic and non-clastic. Clastic, when I say clastic, I want you to think fragment, broken. Okay? Clastic rocks are made from the mechanically weathered, broken down physical pieces of other rocks. Non-clastic sedimentary rocks are, well, everything else. Okay? So the things that are made from the tiny dissolved components of non-clastic rocks. Okay? So not non-clastic, of chemically weathered rocks. Okay? So non-clastic come from the precipitating dissolved stuff from chemical weathering. That's a major component. Also, you can get non-clastic rocks formed as a result of organic material. Okay? Life can, through its processes, form non-clastic sedimentary rocks. As an example, you have rocks made entirely out of fossils, right? Like shells. Have you ever seen a rock made entirely out of shells? Oh, you're going to see it today. I'll pass it around. Okay? We'll talk about that. What about a rock made entirely out of compressed plants? Do you know what we call that? A non-clastic sedimentary rock made entirely out of compressed, super pressurized plants. Plant matter. Coal. That's what coal is. Have you ever heard of coal before? Yeah? I was that weird kid who always wanted coal in his stocking because I wanted it in my rock collection. I never got it, though. Sad day. Okay, so those are your two different types of non-clastic rocks. Your chemical, so things that come from that reform out of dissolved material from chemical weathering, and organic, or you'll see me kind of use the term organic kind of loosely right here, and then I'll define it into maybe biochemical later on, okay? Which includes plant matter and the shells and skeletons of animals that make their shells and skeletons out of chemically weathered products, okay? Let's start off by talking about clastic rocks, though. Clastic sedimentary rocks are commonly formed from, the most common ingredients in these are quartz and clay. Ready for another logic train? Let's do it. Why would quartz be a common ingredient in clastic sedimentary rocks? What do we know about quartz? It's great for using in countertops. Why? It's harder than most other minerals. It's a 7 on the Mohs hardness scale. There are definitely minerals harder than it, but it's harder than most others, which makes it great for countertops. Perfect. Thank you. Now, why does that tie into this concept of quartz being a very common mineral in clastic sedimentary rocks? Jasmine helped us out a lot here. She gave us our first clue. Someone else, help us along. She pointed out that quartz is harder than most other materials. Follow that logic.
How is quartz made? Like, is it through pressure?
Quartz is an igneous. It comes from at the very end of a magma chamber's life cycle, and when it's in its felsic stage is when you'll make quartz. It comes from felsic composition from magma. But that's kind of going a little too far back. We already have all the information that we need to continue this moving forward. Quartz is what? Jasmine just helped us figure out that quartz is what? It's what? Strong. Hard. So what does it mean? I mean, you can use it to break other minerals, but I like where you're going with this. I mean, no one has to choose to use it to break other minerals. What happens to other minerals, though? Sure, but at what rate? What's going to break down slower? Why would quartz break down slower? Harder, and remember what we learned about Bowen's reaction series? About how certain minerals form at certain temperatures and pressures? Right? Quartz is one of the last ones to form. Low temperatures, like relatively speaking, and low pressures, relatively speaking. I'm still talking like 400 degrees Celsius here, but you know what I'm talking about. Low on that end of Bowen's reaction series, but a heck of a lot closer to the conditions up here than, say, olivine forms at 1200 degrees Celsius, right? So quartz not only is harder than most other things, it's also more stable up here than most other things, which means how quickly is it going to break down? You're shaking your head. Put it in words. Huh? Slower. Yeah. Quartz is harder and more stable up here, therefore it breaks down slower. So why does that mean it's a common ingredient in sedimentary rocks? Now someone put it all in words for me. One short sentence. All right, I'll give you this one, but just wait. I'm gonna ask for this back, okay? Quartz is a common ingredient in clastic sedimentary rocks because everything else breaks down faster. Okay? Everything else breaks down faster. It's harder and more stable up here, so everything else pretty much will break down faster, and so quartz is very common. Now, this is where I'm gonna want more from you since I gave you that one for free. Why is clay so common in sedimentary rocks, clastic sedimentary rocks? Why is there so much clay up here? I mean, yeah, it turns into mud, but that's not why there's so much of it up here.
Because of the weathering, right? Because of weathering of rock.
Weathering of what? Can you guys remember what type of mineral weathers down into clay? You're on the right track. I just need to know what the mineral is. It's all information we've already had. We just need to make sure we know where to find it in our notes. Because what if a question like this comes up in an exam? You need to know where to find that info, right? What silicate in particular? You're right, but what's feldspar? Bingo! Feldspar is a light silicate that is the most common source of clay when it weathers down. How much of our crust is made out of feldspar? It's a statistic I gave you in lecture 1. Well, and lecture 2, I think I brought it up. Huh? A lot of it. About 50% of our crust is feldspar. Feldspar weathers down into clay. Boom, bada boom. Clay, very common ingredient in classic sedimentary rocks. Does that logic make sense? All this information we're learning, lecture upon lecture, building upon itself to answer these questions. Okay? Questions that you no doubt lay up at night, staring at your ceiling, wondering about. Why is there so much quartz in the world? Now you know, and you can go to sleep. Okay? Okay, thank you. All right, so that's not to say that every type of sedimentary rock is going to be one uniform substance. It's not all going to be quartz. It's not all going to be clay. It's not all going to be this or that. Oftentimes, you'll actually get some kind of intermingling there. So if I in the future say this is a quartz sandstone, think it's mostly quartz. But there's no doubt some other stuff in there. A little bit of clay, maybe a little bit of calcite, things like that. Very rarely do we find any type of sedimentary rock that is 100% one thing. There's a lot of mixing that goes on. When you look out in the ocean, do you think to yourself, wow, that's a very stratified, very separated substance? No, stuff gets mixed up together in the ocean. It's basically a soup. Okay, yeah?
Is there ever actually anything that's 100%?
Very rarely. Very rarely, but yes, possible. You need the right circumstances for that to happen. Usually a very calm environment where there isn't a lot of energy in the water to mix things up. Okay? Okay. Okay. Now that we've identified that we're looking at a classic sedimentary rock, it's clearly made out of pieces of other minerals, okay? Now let's talk about how we classify the classic sedimentary rocks apart from each other. The first thing you're going to look at is particle size. That's the grains inside of your rock, okay? And for the lab, I give you in each of your test kits, there are little grain size charts there for you to hold up to the rock. And for those of you that are doing this online, for each sample, I give you a picture of that sample up against one of those grain size charts so you can cross-compare, okay? So grain size, anything smaller than 1/256th of a millimeter, microscopic, right, is clay. Anything larger than 1/256th of a millimeter, but smaller than 1/16th of a millimeter, is called silt. You have to have very good eyesight to be able to pick out the larger grains of silt. Anything from 1/16th to 2 millimeters is called sand. Anything larger than that is a granule, and then a pebble, and then a cobble, and then a boulder, depending on its size. You have this chart for reference as well on your Lab 3 PowerPoint, if you would like to use that. So your clays and your silts are going to make claystones and siltstones, or shales. We collectively tend to refer to those as mudstones. Those are pretty much, mudstone is kind of a generic term. Shale is also kind of a generic term if it has layers to it. But claystone and siltstone are the specific names of classic sedimentary rocks made with those sizes of sediment. Sandstone, what grain size do you suppose sandstone is made out of? Sand size. Yep, and that's where the term sandstone comes from. Okay. Now, once we are in using sizes mostly bigger than sand, we're in what is called the conglomerate. Anything that is made from those larger pieces, the granules, pebbles, cobbles, etc., that makes a conglomerate. I'll tell you about the 2 different types of conglomerate here in a minute, but that's how we differentiate them based on particle size. Now, there's also some very interesting environmental information that we can get about what conditions were like in the area at the time that that sediment was deposited by looking at particle size. You know when we get sandstorms around here? Who likes the sandstorms we get around here? No? What has to happen for us to get those sandstorms? What causes them? Wind. Specifically, very high winds. High winds have a lot of what? Huh? What's another word for power?
Downstream or
Basic. What's another word for power? Energy. Okay? That's what you're basically trying to say, right? They have a lot of energy. I knew that's what you were going for. I was trying to pull the word out of you. Okay? High energy. Okay? Would that sand be in the air without that amount of energy? No, it would still be sitting on the ground. It's only because of the energy in the air through that wind that it gets pulled up and blows in your eyes and you hate it. Okay? Using that same concept, apply it to water now. What can the size of particle in my sedimentary rock tell me about the environment at that time?
how much water was in there?
Not how much water, how much what the water had.
Salt.
Huh? Energy, yes. If my water is flowing with a lot of energy, which means really fast, right, typically, it's going to be able to move smaller or larger grains. Well, both. If it can move larger grains, it can move smaller grains too, right? If I have very low energy water, is it going to be able to move those larger grains? No. So, by looking at the size of the particle that was deposited by the water, or wind in some cases, that can give me an approximation of an idea of how much energy was in the system. If I'm looking at a conglomerate, I know I'm looking at a high energy water system. If I'm looking at a fine-grained claystone, low energy system, because no large grains are present. You follow that there? So we are actually figuring out information about rock, about not just the rock, about the environment 100 million years ago when the sediment for that rock was deposited. Okay? These are some of the ways that we gather clues about Earth's history. Okay? So that's particle size. Sorting. Sorting is how many of those grains are approximately the same size. So do I have grains that are all 2 millimeters? Or do I have a whole range of grains from 1/36 of a millimeter to 4 millimeters? Okay? That is sorting. A poorly sorted classic sedimentary rock is one that has a lot of different grain sizes in it. A well-sorted sedimentary rock is something that has the same grain size in it for the most part. Okay? The vast majority of them are the same grain size. What does grain size have to do with it? How can we interpret something about the environment by looking at grain size? I'll give you a hint. It has to do with the energy again. Not the weathering, but weathering is happening as this goes on. We'll talk about that in a minute, okay? How much, do I need a lot of energy or low energy for big particles? If I have low energy, what can I move? Small particles. But what if I have big and small particles in the same rock, which was made from the same layer that was deposited by that water? What does that tell you? You must have had high energy at one point, but then what happened? If I lose energy slowly, so let's say I start off with high energy, okay? I'm up here. I'm moving all sorts of sizes. But let's say that I start to lose a little energy as time goes on. I drop a little energy. What falls out of my water? The biggest pieces. They form a layer of well-sorted, large-grained sediment this way. A little further downstream, I lose more energy. What falls out? The next size down. Say my medium-sized particles. I get a layer of medium-sized particles making sedimentary rock over here. Then, even further downstream, what do I still have left? My small particles. And those fall out as I gradually lose my energy. As I slowly lose energy, I lose different types of different sizes of sediment as time goes on. So I'm going to have distinct layers of those different particle sizes. But what if my layer has all of them? Oh, it lost energy. But how quickly did it lose energy? For me to have all grain sizes present in the same layer of rock, I must have lost energy like that. High energy to move all that stuff, lost energy like that, so it didn't have time to separate. It all dumped out at the same time. That's an unsorted sedimentary rock. So now we're figuring out events, the time it took for me to lose that energy. If I lost it slowly, I'm probably looking at a low angle, maybe kind of meandering sort of stream thing. If I lost it like that, I'm probably maybe looking at a landslide or a mud flow or something. Okay? Some high energy event that caused all of this stuff to get picked up, and then it reached the bottom of a hill, like at the bottom of a mountain where that often happens, lost energy like this, and it all fell out. I can make interpretations based upon sorting. Okay? That makes sense? Great. All right, next up we got shape. Now someone brought up weathering with concept of sorting. Weathering doesn't have to do with sorting, but it does have to do with the shape. I can have highly angular materials, grains, or highly rounded materials or grains. What would determine that? Weathering. You remember how weathering takes off corners before everything else because corners have more surface area? So we go from a highly angular grain when it's a fresh weather or a freshly broken piece to a highly rounded or spherical, in some cases, grain if it's experienced a lot of weathering. What interpretation can I make about my sediment by looking at the rounding of it? The rounder it is, what must have happened? Huh? Maybe a lot of wind, maybe a lot of water. Over a lot of time or distance. My interpretation I can make from this is my rounder grains, the smoother my grains are, the more time it had to weather before it became part of that rock. So if I'm looking at a highly spherical, then I would say this probably came from a source far away, or it stayed here and got moved around a lot by stuff before it finally got incorporated into rock. Okay? Give me a second. One of our IT guys just poked his head in. He might need to talk to me. David, did you need me? David! He's an old guy. He can't hear me. He's only like 40 feet away. He keeps walking. Okay. And camera, following me. Good. Okay, so any questions about these characteristics of clastic sedimentary rocks? Great. So now, let me introduce you to some of the more common ones. All right? This is shale. Have you guys ever heard the word shale before? Where have you heard the word shale before? Okay, so shells are different. Shale is what I'm talking about. S-H-A-L-E. Shale is a type of clastic sedimentary rock made from very fine to fine grains. It means clay to silt-sized particles. Okay? Shale is one of those mudstones I talked about earlier. Okay? Shale is the kind that forms in very thin layers. Layer upon layer upon layer upon layer upon layer upon layer. Tiny little layers. Okay, we call them laminations. When I pass this around, you'll be able to see a few of them. I think I actually have, yes, I have this one as well. It'll be easier to see the laminations in this one, at least for the camera. Okay. So you can see the laminations, the very thin layers in there, right? Almost paper thin. Okay. So what happens here, if we're talking about fine and very fine grains, what kind of energy must we be talking about? How much energy was in the water? Very low. Very calm water. So you'll typically find shales form at the bottom of the ocean, at very deep lakes, even on floodplains. Now you're like, wait a second, floodplains, we're talking about floods. Aren't those pretty high energy? They are when there's a flood. But what about when it's just kind of gently running water over the floodplain? It drops out the small stuff, okay? So you get floodplains that can have mudstones built up in them as well. But most of this stuff comes from the bottom of the ocean or other deep bodies of water like lakes and things like that. Okay. Now the color that you get from a shale depends on, as with so many other things, what else is in there. You can get red shales with a high amount of iron. You can have green shales with a high amount of chlorite. You can get black shales like this with a high amount of carbon. What might add a lot of carbon to this? Life. Bingo. In particular, we find black shales form very commonly at the bottom of the ocean. Is there a lot of life in the ocean? Oh, you have no idea. If you were to go out to the ocean and you take a mouthful of water, you're drinking all sorts of tiny little things. Planktons, zooplanktons, coccolithophores, radiolarians, diatoms, foraminiferans. All the tiny little critters that live on microscopic lives in the ocean column. They live, they die. Where do they go? Bottom of the ocean. Get incorporated into the sediment. That sediment turns into rock. Some of that rock becomes black shale. Black shale, high in carbon, is a very common source rock for oil. Black shale produces a lot of oil and natural gas. We like this stuff. Okay? There you go. Next up, sandstone. Sandstone comes in a couple of different flavors. I say that, but don't try to eat these. You'll hurt your teeth. Okay? Sandstone is made from, you guessed it, sand-sized particles, 1/16 to 2 millimeters in size. That's really the only thing that makes it be a sandstone. The composition of sandstone can be fairly wide-ranging. In general, though, the most common ingredient is still going to be quartz. You can have sandstones that are almost entirely made out of quartz. This is nearly 100% quartz. Not totally, because like I said, absolute pure one particular thing is pretty rare. But this is nearly 100% pure quartz. You can scratch this on glass. You can do all of the tests to this to see if it's quartz. And it is, in fact, quartz. Okay? It will respond in the same way to all of those tests. So here we have a whole bunch of sand-sized quartz particles that got compressed together and turned into a quartz sandstone. There are a couple of other varieties you can get. When you have a high amount of feldspar in your sandstone, we call it an arkose. This is an arkose sandstone. When you have a high amount of clays in there with your feldspars and your quartz and whatever else is in there, it will actually substantially change the color. It generally makes it kind of a darker gray. This is still a sandstone. It's just called a greywacke because it has a high quantity of clay in it. Okay? So there's lots of different types of sandstone. Those are just the three that I'm taking the time to teach you about in this class, okay? There we go. Yes? You can use the restroom. Yeah. Okay. Then we've got conglomerate. Now I promised you earlier I'd show you the two different types of conglomerate. Where's my, there it is. Conglomerate is a word that generally refers to poorly sorted, large-grained classic sedimentary rocks, okay? So this right here, that's a conglomerate. This is also a conglomerate, but there are some differences here. Here are the two types. Your true conglomerate, which we just call conglomerate, is made of rounded grains. When you look at this, you'll see all the grains in there are nice and rounded before they got incorporated into this rock. This is a type of conglomerate where all of the grains are angular, meaning that they had barely any time to get weathered before they got incorporated into this rock. We call this type breccia, B-R-E-C-C-I-A, breccia. So breccia is the type of conglomerate with those angular pieces. And if it has rounded pieces, we just call it conglomerate still. Okay? Breccia conglomerate, or breccia on my right hand right there. All right. Questions about clastic sedimentary rocks? No? All right, well then let's talk about some chemical sedimentary rocks, aka non-clastic. So now I'm going to separate our chemical ones apart from each other like I told you I would, into inorganic and organic, okay? So you've got your inorganic, chemical, non-clastic sedimentary rocks. Yes?
So I was gonna ask this earlier. So
Sure.
you said something about the like in the chemical that it's formed from like the precipitate from the other things. So in my chemistry class I took last semester,
Yeah.
we also made precipitates. If we were to have let those like particles, say, would they have turned into something like this?
That's the same process I'm talking about, but they would not have become a rock as a result of your experiment. You can grow crystals that way. If you've ever grown a crystal in a jar, it's through this process, but you've grown one crystal. You haven't made a rock out of a bunch of crystals.
Okay.
Okay?
Because I remember we made some iron crystal.
Yeah.
It was green, so
Oh yeah, totally. You can grow all sorts of things that way. It's really fun to have those experiments. I would love to have the kind of time to do that, but to do it right would take most of the term, and it would take a while, a whole day to get everyone set up with that. So I kind of weighed it, and hawed over it, and I decided in the end it wouldn't really be worth it to have everyone do a crystal growing activity when it wouldn't even pay off until finals week, you know? Okay. Where am I? Oh, yes, inorganic. Okay, we're talking about inorganic. So inorganic, non-clastic, sedimentary rocks form through that precipitation we were just talking about. So remember that when we dissolve a substance, it kind of falls apart chemically and gets incorporated into the fluid we dissolved it in. But what happens if we evaporate, say that water, if that fluid is water, which it commonly is, over time? Eventually, the concentration of my dissolved substance increases. Our remaining fluid becomes enriched in that stuff. And eventually, you reach a point, a threshold, where there is not enough water for my substance to remain dissolved. And so it's going to start reforming the crystals that it dissolved from in the first place. So when that happens, those crystals, when it happens, say, in the ocean, those crystals, they will form in the water and then slowly sift down to the bottom of the ocean and form layers of that chemically originating sediment, okay? And then those can become layers of chemical non-clastic sedimentary rock, inorganic stuff. So this is an example of that. This is a type of limestone. Limestone is something we will talk more about in a minute. But this is a type of limestone, okay, that forms from that, that precipitating action, okay? Now, limestone is very interesting because it's made from calcite, and calcite does some weird stuff. We talked a little bit about how weird calcite is. Here's another interesting weird fact about calcite, if I haven't told you this already. Normally, when you want to dissolve something, you'll put it in warm water, right? Calcite dissolves easier in cold water. Did I already mention this? I'm teaching multiple sections. It's hard to keep track of who I've told what, okay? Calcite dissolves easier in cold water, which means that I'm not going to get this in cold water. I will get this in warm water. You know, another cool way that we can use that information, when I'm looking at shells, seashells in layers of rock, I can tell approximately whether I'm looking at a cold water region or a warm water region, because my little tiny animals will make their shells out of silica in cold water because calcite will dissolve. And they'll make their shells out of calcite in warm water because calcite is more stable in warm water. So I can, by just looking at the chemistry of the shells, I can get some environmental approximation of water temperature at that point in time. Very interesting. But yeah, so this is a type of limestone that we get from that. I'll pass that around in just a minute when we talk more about limestone. But then you get organic. Now, the word organic is tricky. You guys know what organic means? Huh? There's a lot of different definitions for the way we use organic these days. Okay? Organic technically means that it has a combination of hydrogen, carbon, and oxygen in a structure typically formed by the presence of life. But you can simplify that to simply mean life. Those are not actually the same thing, but society is a thing, and society reads into it. So when I say organic, what I'm not saying is all of these things are pieces of something that was once alive. There are definitely sedimentary rocks that are. For example, coal. Coal is absolutely an organic rock. It's literally made out of pieces of plants. Shells, though, are made by the animal using inorganic ingredients. So it's a tricky gray area. I'm throwing them in here under organic. In other places, you'll see them labeled as biochemical. Some people just straight up call them inorganic. It depends. For simplicity's sake, though, I'm throwing them here in the organic territory because an animal made them. Okay? So, now let's talk about limestone. Limestone makes about 10% of all the sedimentary rock on the surface, which is really impressive when you consider that so much of it does in fact come from the presence of life in one way or another. Okay? So you can have well, I'll just use this one since I'm already here. Okay? This is a type of limestone that is formed through precipitation. So when I have a warm, shallow sea, I'm going to get little pieces, little chemicals of calcite that form in the water, filter down to the bottom of the ocean, and then form layers there. Okay? And that's going to give me this type, this not evaporative, but precipitative type of limestone. That's the inorganic type, by the way. Then, let's see, let's get this one. And, there it is, this one. Okay. Then, you can have reef systems. Do you guys know what a reef is? Someone give me tell me what a reef is, just real quick. Like what? Kind of like plants in the ocean? Sure, with the exception that they're pretty much all animals. Coral is an animal. Did you know that? Yeah, pretty much everything that forms a reef system are animals. Algae, those are more like plants. They're closer related to plants than they are to animals, but coral are most definitely animals, as are most of the other things that make your reef. There grow shells, exoskeletons, endoskeletons in some cases. But they grow layer upon layer upon layer, generation upon generation upon generation, building on each other, making these vast mountains of animal-grown mass. Okay? And they just grow on top of each other for hundreds of thousands, even millions of years at a time. What happens to those? Well, eventually they die. These coral reefs will eventually die, usually through some climate change that occurs. We'll talk more about climate change in the future. Just know climate change has happened for a very long time, long before humans came around. We don't cause climate change. We have caused influence on climate change in our day and age, but climate change has happened on our planet for literally billions of years. Okay? Normally when that happens, it'll kill off a bunch of stuff. There will be an extinction, and that extinction will often cause coral reefs to die. Well, when those coral reefs go through the process of getting heated and pressurized and turned into rock, it makes fossil limestone. This is fossil limestone. You can see the shells in there. Okay? This is made out of calcite. You can drop acid on this and it will fizz, just like your normal calcite will. Now, have you guys ever been out to the Guadalupes? This picture I have up here on the screen, that's a picture of the Guadalupe mountain range, just out in New Mexico, not far from us. You should take a weekend, go and camp out there, or hike. It's amazing. I go camping or caving in the Guadalupes every now and then. It's a great time. That entire mountain range is a fossilized coral reef. Tells you how big they can get. They're huge. Okay? And it's all made from material grown by animals in a coral reef complex. Then you get another type of limestone. Well, it's on the wrong table, that's why. Okay, you get another type of limestone made from the broken pieces of shells that kind of get washed up on your beach. Okay, we call that calquina. Think of this as kind of pre-fossil limestone. Okay, it's still gone partly through the process of becoming that fossil limestone. It's all compacted together, but you can totally tell. It kind of looks like a Rice Krispie treat, right? You kind of want to eat it, don't you? Careful. If you feel the inclination to eat rocks, you might be a closet geologist. Okay, so these are all the little pieces of shells washed up on the beach that have gotten fused together and pressurized together. Then we've got chalk. You guys ever used chalk? You like, the painting with chalk or playing with chalk when you were a kid? You know what chalk is? Real chalk. I'm not talking about the chemical stuff that they make now. Real chalk like this, like what you see in that picture on the screen over here. This entire cliffside is made out of chalk. These are the White Cliffs in England. That is all chalk. And that's a lighthouse right there for scale, by the way. Chalk is made by hundreds and hundreds of trillions of microscopic animal skeletons. All those little things I listed for you earlier, the planktons, the foraminiferans, diatoms, etc. They live, they die, they fall to the bottom of the ocean, and their skeletons going to make chalk. When I rub some of that off and I see that dust on my fingertip, I've got hundreds of thousands of tiny little skeletons on my fingertip right now. Think about how many of these things have lived over time to make this rock and that cliff. It's a lot of living things in the ocean, guys. Like, you have no idea how many things live in the ocean and have lived in the ocean. There are time periods in Earth's history when the amount of things living in the ocean, you would not believe. Like, you go step in the ocean and be like, everything, just like, looks like just movement around you everywhere. You drink it, it's like the nutritional value of soup because there's so much stuff in it. Okay? Lots of living things in the ocean. And they make chalk, these microscopic things, when they die and they get compressed together. Any questions about limestone? Actually, there is one more type of limestone I want to show you. You remember when I said that you get that inorganic limestone when the crystals form, they fall to the bottom of the ocean, and they get compressed together? Well, sometimes when that happens in water that is shallow enough for the wave action to go back and forth, it's going to take those calcite crystals and wash them back and forth and back and forth. And they're going to slowly get bigger and bigger as they pick up more calcite. But the washing back and forth motion is going to kind of make them grow into this sort of smooth, rounded shape. We call those oolites. This is a bag full of oolites from the Bahamas. There's kind of a leak in there, so just be careful. Don't hold this over your laptop or anything. But these are tiny little oolites. They kind of look like sand. When they get compressed together, they make oolitic limestone, which looks very much like sandstone. How might we test whether or not this is sandstone or not? Hydrochloric acid is a great test. What's another great indicator to tell if it's made out of quartzite or calcite? Or quartz or calcite? Huh? I mean, being cold or hot doesn't make a difference for them when they're in a rock. What about a hardness test? Calcite, hardness of 3. Quartz, hardness of 7. Camera, what are you doing? Hello? Hi. Yeah, there we go. All right. Anyways, you can do a hardness test, you can do a hydrochloric acid test, and that's how you would be able to tell a difference there. All right. Some other chemical rocks that you might come across. Dolostone. Do you remember how we learned about calcite and dolomite? Both of them react to hydrochloric acid. Calcite will do it right away. Dolomite does it if you powder it, but they look almost identical otherwise. Very hard to tell the difference between the two. Well, dolomite is the same way to limestone. Dolomite is made out of dolostone is made out of dolomite. Excuse me. And it's still trying to figure out how exactly that happens, because their characteristics are so similar to each other. The only difference is there's some extra magnesium in a dolomite. That's the difference between them and a calcite. That's why the magnesium kind of gets in the way. It interferes with that hydrochloric acid reaction a little bit. So there's lots of theories as to how dolomite even forms in the first place. That it starts off as calcite, has some magnesium introduced to it, possibly through the introduction of some warm water or something. Magnesium kind of latches onto the chemical chain there. And then you get layers of dolostone instead of limestone. And it's just kind of a weird coincidence, kind of a weird circumstance, not a coincidence. It's a weird circumstance, okay? So we're still trying to figure out how exactly that works. It's a tricky thing to test, though, because it's a thing that the transition of one type of rock to another is something that happens over long periods of time. So what do? Take a layer of limestone and then introduce some magnesium-rich water to it and then wait 100,000 years? It's not really practical to test like that. So right now there's just pretty much just theory on it. But nevertheless, dolostone, still a common thing that we find. Chert. I've talked about chert. Chert is microcrystalline crystals that form, and you can form agates and geodes and stuff out of it. You can get just layers, whole beds, entire layers of chert. Some other words for chert: flint and jasper. You may have heard of those terms. We like calling it jasper when it's going into jewelry or some other fancy, what's the word I'm looking for? Decorative object, okay? Chert and flint are often used when we're describing how people will nap it. They'll break it into like arrowheads and spearheads and things like that. Native Americans have done that for thousands of years, okay? Some other chemical rocks: evaporites. Evaporites are any material, any sedimentary rock that form as a result of the evaporation of water. So salt, for example, salt and gypsum. Any of you guys ever been out in Utah? You ever driven through Utah? If you ever do, take sunglasses, because a lot of Utah is really wide and flat, and it's covered in this crust of white rock, just like this. This is a picture that you will see in Utah very commonly, and it can be very blinding in the sunlight, which is why I say sunglasses. But that's just a layer of salt and gypsum left behind, because Utah used to be mostly covered in a giant lake. There used to be a giant inland sea there, actually, which gradually, during the time of the dinosaurs, closed off from the ocean and started to evaporate away. And then finally, by the time about 10 million years ago, had shrunk down to just kind of a big lake. And that lake, which we call Lake Bonneville, finally finished evaporating away a couple tens of thousands of years ago. And now all we have left is the Great Salt Lake. When you look at a picture of Utah, there's just a big old lake in the middle of it. That's the Great Salt Lake. That's all that's left. And it's very, very salty, hence the name. All right. Then we have coal. Coal is made when plants fall down into water that is anoxic. Do you know what anoxic means? Lacking oxygen. If oxic means has oxygen, anoxic must mean lacking oxygen. Thank you. Okay. It is anoxic. How does it get anoxic? Well, let's say you've got a place like a swamp or a bog or a marsh or something like that, where you have water that just kind of sits there but does not get refreshed very often. All the little microorganisms that live in that water are going to be eating the dead plants that fall down into that water. As they do so, they are pulling oxygen out of the water. As they do that, the water becomes anoxic, and because it's not refreshed very often, you don't get much oxygen in there. So now we have an anoxic environment. In an anoxic environment, decay is significantly slowed down, or non-existent, depending on how anoxic it is. So you'll get plants that fall down into this water, layer upon layer upon layer upon layer upon layer upon layer, and they just pile on top of each other thicker and thicker and thicker and thicker. But they can't decay away. They don't rot away entirely. That takes you to compressed plant matter called peat. This is what peat looks like. P-E-A-T. You can see how it is clearly still very planty, right? There's obviously a lot of plant matter going on in there. Well, when you take that peat and you bury it deeper and you heat it up and you pressurize it even more, that gives you lignite. It takes about 3 feet of peat like that to make 1 foot of lignite like this. This is lignite. Now we're looking like a rock. But when you look at it, you can still see that there are some obvious pieces of plant in there. Impressions of leaves and sticks and things like that. Okay? This is lignite. Now you can burn peat. It burns very quick though. Not very energy efficient. But when you make lignite, you're taking all of the energy potential in that peat. You're compressing it down into a smaller package. You're getting rid of some stuff. You're getting rid of some sulfur. You're getting rid of some other things that you really don't want to breathe in when you burn stuff. But you're making all that energy compressed into a smaller package. Lignite will burn. It takes more energy to start it burning, but once it does, it releases more energy than it took to start it. Okay? So now we're talking about lignite. We're talking about very efficient fuel sources. Okay? That is lignite. Then if you take that lignite and you compress it down even more and you squeeze it, that gives you coal. What we typically call coal is actually called bituminous coal. And again, it takes a few feet of lignite to make something like bituminous coal. Bituminous coal, very energy efficient. Still has some byproducts, sulfur and a few other things that we really don't like putting out in the atmosphere. So coal has gone from being the main fuel source of the world, which it was during the Industrial Revolution. We owe the Industrial Revolution to coal. Okay, it has gone from that to, we still use a lot of it, but it's highly regulated in most places now, especially in the US. Okay, we still rely on it, but you have to go through a lot of hoops to clean up your mess as you burn it. Okay, but this is coal. Now, for most people, as far as they're concerned, that's where the process stops. There is actually one more step after bituminous coal, though. If you take bituminous coal and you metamorphose it, you get anthracite. Now, we haven't talked about metamorphism yet. We'll talk about that next time we meet. But let's just say for now, you add a lot more heat and a lot more pressure. You condense that energy even into an even smaller package. You remove even more of the nasty stuff that you don't want to burn. Here's the anthracite. Anthracite is quite possibly the cleanest natural fossil fuel out there. It burns very clean. So the question is, why don't we use it more? What do you think? Why wouldn't we use such a clean source of fossil fuel? Good thought. No, it's not that it takes a lot of energy to start it burning. Once you start the process,
Is it more costly to?
why would it be more costly? No fossil fuel is reusable.
Like it's,
Deeper?
or like,
It's formed through metamorphism, which happens at high heat and pressure. Where do we get those conditions, do you think? Deep underground. We have so little anthracite at the surface, we cannot use it as a commercial fuel source in most places. So, bituminous coal, with all of its gases that come out as a byproduct, is the answer, or has been for a very long time. All right. Any questions about those rocks? Okay. Let's talk about diagenesis. I promised we would. Here we are. Diagenesis is any change that happens to my sediment after deposition, but before metamorphism. Remember, metamorphism kicks in once you hit a certain heat and pressure. Well, what heat and pressure is that? We'll talk about that on Wednesday. For now, though, diagenesis typically will occur between 150 and 200 degrees Celsius, and after you are a few kilometers underground. What are some things that can happen in lithification? Fossilization can happen as a part of diagenesis, and lithification, which is a process by which sediment becomes sedimentary rock. You take loose sediment, squeeze it, compress it, you get a rock out of it. Okay? So we take our sediment and we compress it. Okay? Called compaction. Okay? You compress it and you squeeze out a bunch of air and a bunch of water, and then something called cementation happens. As you're squeezing out that water, the dissolved stuff that was in it is left behind. Maybe it's an iron oxide or calcite or silica or something. But as it's left behind, it makes kind of a cement that holds those grains of sediment together. We call it cementation. So the combination of compaction and cementation is what takes sediment and turns it into sedimentary rock. We call that process lithification. Give you all a second to catch up there. So that one, that's the anthracite. That's actually going to go right there on the empty tray right there. Yes, sir. Thank you. Okay. So what have we learned? We've learned that we've got clastic and non-clastic, or chemical, if you prefer, sedimentary rocks. We can tell those rocks apart from each other. In the case of classic sedimentary rocks, by particle size, rounding and sorting. And in the case of non-clastic sedimentary rocks, things like its texture. Is it made out of fossils? Is it made out of crystals? Okay. Is it organic? Is it made out of plants? Things like that. Okay. So we can use all this information to make interpretations about Earth's history. We know how to look at what a sedimentary rock is made out of and make interpretations. We also know how to look at igneous rocks and what they're made out of, and their grains and their crystal sizes and things like that, and make interpretations. So we have a lot of powerful tools to interpret Earth's history already. But now I'm going to tell you a little bit more about how we can find out more about these environments. When I say environment, what am I talking about? Well, we've got swamps, we've got deserts, we've got deep seas, we've got beaches, we've got all sorts of environments on the surface of our planet. Just by looking at the layers of rock and the clues that have been preserved in them, we can put together paleointerpretations. That means ancient historical interpretations of the history of our planet. Like, have you ever looked at a picture of a dinosaur? Like some artist has drawn a dinosaur, and they have certain plants there, and there's a mountain or a volcano in the background. A lot of that's probably made up, but how can we have an idea of what it was actually like? By finding out stuff like this, by learning things like this. Sedimentary structures are evidences, pieces of evidence from that environment, of things that were happening in that environment that gets preserved in the sedimentary rock. For example, ripples. Ripples can be preserved in sedimentary rock. What does a ripple tell you? Or a whole bunch of ripples like this. How do you get ripples in sediment? Water doing what? Flowing. Yes. Water was flowing. And I can even tell what direction it was flowing by the angle of my ripples. Fascinating. What do those look like? Whatever you think it looks like, it's probably that. I mean, yes, it's rock. Mud cracks. That's mud cracks that have turned into rock, have been preserved. What does that tell you? There was water here. It dried out, leaving behind some probably dry lake bed or something, right? Where once there was a lot of water, now there's none. So we can make interpretations based on these things. Bedding. Bedding is a word that I've used before. Bedding is a term we use to describe different layers of rock that have separated from each other for some reason or another. Here you can see many different beds of rock separate from each other. This might all be the same type of sandstone, but with slightly different characteristics. This might be slightly smaller grain size than that one, which is why they're separate from each other. Okay? It might have a different cement or a different quality of cement. They might not be as well compacted together. Some difference is causing them to be separate from each other, making those beds. Something was different about the environment. Okay? This, when you have all of these different layers stacked on each other at an angle, you see how all of these different angles, this angle changes over and over and over? Can you think of any environment where sediment can get deposited at an angle, but that angle constantly changes over and over and over? What do you suppose that change in angle means, by the way? Huh? Wind doing what? Yes, it's blowing, but what's it doing? What do you think? What were you going to say? Yes. Each one of these represents a different time period. Something changed between each one. What do you think it was? They're deposited at an angle. Something's depositing them. Something's shoving each one of these layers on top of the other at an angle. And then that angle is changing. That's what's making these different layers. The angle of deposition is changing. Maybe it's this way, then it's this way, then it's this way, then it's that way, then it's that way. What might cause that? What kind of environment might we find this in? It's okay, I don't expect you guys to be geologists immediately. I was just wondering if you could reason it out. You were going in the right direction with wind, PJ. Yes. What environment might have wind piling sediment up at an angle this way, and then another angle this way, and then another angle that way? Huh? No. Huh? We have an example of this much, much closer than any mountain or valley. You know what I see when I look at this? I see a dune blown this way, and then another dune blown on top of it at that direction, and then another dune blown up at it on top of that. We call this crossbedding, and it's very common in deserts, where the wind changes direction and piles dunes on top of each other. You can also get this, by the way, in places like rivers, where rivers will often run over on top of other old rivers that used to be there, depositing on top of their deposited sediment, things like that. Anywhere where a fluid is pushing sediment at an angle up on top of another layer of sediment that was pushed up there by a previous thing. Crossbedding is what we call that. And this screams desert to me. This is a desert dune environment when I'm looking at that. So by looking at the world we have today and observing it, we can make interpretations about the things that happened back then. Fossils are also things that we can find plenty of in as evidence of surficial processes. These are all fossils that I have found at one point or another. Actually, all the fossils that you see here, with the exception of this bottom one here, I found in Montana. These are all fossilized trees that I found in Montana. Some of them I have up here. This is a Tyrannosaurus rex rib that I found in Montana. These are pieces of Triceratops skull, the eyebrow section of a Triceratops skull that I found in Montana. The sad story of this picture is I got so excited that I found these pieces. I took a picture, put my camera down, and then started moving all the pieces away. And underneath the pieces of the eyebrow, I found the rest of the skull. And I started uncovering it, brushing it away. I got a couple square feet exposed, enough for me to know, oh my gosh, the whole skull is here. But it was the last day on my permit. To dig for fossils anywhere, you need a permit from either the federal government or the agency that is in charge of that, Bureau of Land Management, Forestry Service, whoever is in charge of that parcel of land. That was the last day of my permit, of course. So I didn't have enough time to uncover it. So, I mean, that whole afternoon, I was just ecstatic. So I uncovered it, and then I realized I didn't have enough time. So I covered it back up, and then I put a tarp on top of it, and then I notified the university, the nearby university, hey, I don't know if you have a dig coming out here anytime soon. There's a Triceratops skull here. You should come get it. I completely forgot, in all the excitement, to take out any pictures of it with my camera. So the picture of the eyebrow pieces I have on top of the skull is the only piece that I've got. It's the only picture I've got of it. So typical. Anyways, this is a turtle shell that I found in Utah. So this is my non-Montana picture here. These are all from Montana. This one is from a dig I went on in Utah. That is a turtle shell about that long, about that wide. Okay. A lot of non-metallic, we do get some metallic resources from sedimentary rocks to be sure, but a lot of non-metallic resources will come from sedimentary rock. For example, limestone. Limestone, we will often crush it and use it as aggregate. Have you ever gone on a dirt road or been in someone's driveway and it's just covered in kind of crushed gray rock? That's most of the time that is limestone or dolostone. Okay. We use it a lot as building material. Our floors and walls and everything in this bathroom down the hallway, that's travertine, or it's probably fake travertine if I'm being honest, but it's supposed to look like travertine. Travertine is a type of limestone. Okay, we use limestone all the time as a construction material. Gypsum. Have any of you ever done any construction with drywall? Yeah, you know the white powder in drywall? Yeah. That's gypsum. That's powdered gypsum. It's meant as it kind of absorbs water to keep it from getting in your house or whatever you're building. Okay, it's meant to keep the water out, the humidity. Okay, these are a bunch of other different types of materials that we get from sedimentary rock that we use in everyday life or industrial uses. Just kind of a picture there. This is the interesting one though. These are all the different resources that we use in the United States. Starting off with our energy. Coal, petroleum, and natural gas make about 84% of all of the energy that the United States uses. Okay? That means that the other 16% is other, which 9% of which is nuclear. Huh? That's where it's at. Nuclear is where it's at. I'm a huge proponent of nuclear. Absolutely agree. We need to go more nuclear. Okay. Only 7% of the United States runs on renewable energy, which includes biomass, which is wood, basically. Okay. Solar is 1%, hydroelectric 34%, geothermal 5%, wind 7%.
What's geothermal?
Geothermal is, you remember how we learned about the geothermal gradient? So the hotter it gets hotter the deeper you go underground. Well, if you drill a hole deep underground where it gets really hot, and then you pipe water down there, what's that water going to do? Evaporate and turn into steam. You can use that steam to turn a turbine. That turbine generates electricity just like a coal power plant would. Except instead of burning coal or natural gas or something to make the steam, you're just using the natural heat coming up from the bottom of the earth, from the middle of the planet. It's great, but in certain parts of the country, you have to go really deep to reach that temperature that's hot enough. In Iceland, it's right at there at the surface. You barely have to go down more than a couple hundred feet because it's so hot close to the surface. Around here, you have to go pretty deep. In like Colorado or Idaho or any of those places up there, you have to go way deep. So it's not a worldwide efficient energy source, which is why we don't use it more. Okay? Hopefully more in the future, but not a lot right now. Solar. How many solar panels do you see out there in the world? Quite a few. We have some solar farms not far from here. There are 2 massive solar fields. I'm talking hundreds of acres of solar panels out in the middle of nowhere about 30 minutes from here. Okay? Even with all of that, with all of the solar panels we see everywhere, only 1% of, it's not just 1% of this, it's 1% of the 7% of the renewable resources in the United States are powered by solar. Solar is not very efficient. It's great, but it costs a lot of rare resources to make, and it's not efficient. A solar panel will only turn about 40% of all of the light that it absorbs into electricity. It reflects most of it because it's a panel. It's a flat surface, right? So it reflects a lot of it and only collects about 40% of it to turn into electricity. So it's not great. But, you know, we do what we do. Wind is a problem. Have you ever seen those towers? Think about the vast quantities of resources that goes into making those towers. Incredible quantities of resources to make each one. And to build it and set it up and maintain it. Takes a lot. So all of our efforts for renewable resources, it's kind of a pick your poison thing. Sure, you have to use less fuel when you use more renewable resources, but think about how many other resources you're using to make the renewable resource. How many strip mines are we going to open to get the lithium we need for all those batteries? Would you rather mine the planet or burn fossil fuel? It's got to be one or the other, or else we collapse civilization. Did you have a comment? Go nuclear. Again, nuclear is a great option. Why is nuclear a great option? We already have a lot of fissile material, and it's easy to make more. It generates energy for a very long time. We have very efficient, very small nuclear facilities now. The 4th generation nuclear reactors that are coming out are very, very good, very safe. Why do you suppose people aren't more on the nuclear train?
One bad time.
Oh, there's been more than one bad time. There's been quite a few bad times. There have been probably a half dozen really bad major nuclear reactor incidents around the world. And then a smaller incidents, many smaller incidents. But it makes people scared. You have one Chernobyl, you've got a 3 Mile Island, you've got a Fukushima, you've got all of these things that happen, and it makes people scared. Not in my backyard, they say. I don't want that to happen. Ignoring the fact that for every one nuclear reactor that's ever gone bad, there have been 400 that went their entire time without a single incident. But it only takes one. Now, people are slowly warming back up to it, especially as the effort to move away from fossil fuels increases momentum, but not nearly fast enough. We're not going there fast enough. Another problem with nuclear power is what do you do with the waste? There's a lot of nuclear waste. To make nuclear fuel, you need uranium-236 usually is what you would use in a power plant, okay? Which is refined to about 30 to 40% enrichment. So you get rods of metal that are about 30 to 40% uranium-236, a radioactive isotope, and then the rest, usually graphite, okay? Or some other material, inert material, okay? And you put those cones, you put those rods of material in your power plant, and they're separated from each other by walls. But then you lift them up out of those sockets and in close proximity to each other, and the radiation from each one slams into the other one, excites each other's radiation, making a ton of heat. It's releasing a lot of radiation, and a lot of that radiation is neutron radiation. That neutron radiation is what causes this cascade effect. You don't want your cones too enriched, or else you'll make a bomb. Okay? But you keep them just enriched enough that you have enough neutrons being made that it'll make a controllable cascade reaction with the other cones in the area, the other rods of metal in the area. You keep a lot of graphite around because graphite has the ability to soak up the extra neutrons and keep them from starting an out-of-control cascade effect and making a bomb. So this is how it works. All that heat turns water into steam. That steam water turns a turbine, which is attached to magnets, which makes your electricity. Okay? Yeah.
Isn't that what the Russians did? That they used like a different wrong material on the rock tips and then made it go like all erratic?
Yes. They were using graphite, but they were experimenting with other types of material as well. And there were quite a number of safety regulations that were not being followed as well. There were some very incompetent, overly proud people. I mean, it's the Soviet Union. I'm not afraid about, insulting anyone from the Soviet Union, right? In the Soviet Union, a lot of people were put in power purely because of who they were or who their parents were, not because of whether or not they were qualified for a job. Which is why a lot of nearly global scale disasters almost came because of appointments that were made. Yes. Anyways, of course, we also owe a lot to some Soviet people. You guys know who Stanislav Petrov is? No one remembers Stanislav Petrov. None of us would possibly even be here without Stanislav Petrov. There was a day during the Cold War, there was a Russian nuclear sub out in the ocean, and its sensors erratically picked up, like it was a fluke, it was not real, but it picked up a missile launch from the United States. It was just a random fluke technological issue, but it picked up a missile launch, and they were under standing orders. If you detect a missile launch from the US, you fire at the US, you take them out, right? That was the whole point of the Cold War. It was called a Cold War because it wasn't a real war. No one was shooting at each other really. But we were fingers on the button ready to launch nukes at each other. Okay? Stanislav Petrov was the guy sitting at that computer, and he had the choice, launch or don't launch. He was a very cool-headed guy. Thank goodness. Anyone else possibly in the whole military, but a lot of people for sure, could have been, launch, I have my orders, beep, launch. And even though the United States never sent a single thing, Russia, that would have been the start of the war, and that would have possibly even been it for everyone. But he was thinking in his head, there is no way that the US just launched a missile. They wouldn't. This is ridiculous, right? He immediately thought to himself, it cannot be real. He did not launch. He did not hit the button. And everyone was screaming at him, hit the button. He didn't hit the button. And they found out it was a technological issue. It was a ghost basically on the radar. And thank goodness he had that much of a cool head. So while I'm critiquing the way that the Soviets did things, we also owe a lot to a few of them. Okay? Everyone's forgotten Stanislav Petrov, but I haven't. Okay. Anyways, yes, we kind of went astray from this here. This is how all of our energy distribution is. Okay? And then we've got all of these. Look at these. 5,713 kilograms of stone, 178 kilograms of salt, 249 kilograms of iron, 35 kilograms of aluminum, 3,700 kilograms of coal, 3,500 kilograms of petroleum. Do you know what all of these things have in common? All of these non-metallic resources? That's how many resources it takes to keep each of one of you Americans in a year. Each of you. Now, you're thinking to yourself, when have I ever used 35 kilograms of aluminum, 11 kilograms of copper, or 178 kilograms of salt? Well, I mean, it's the things that you use in your food, it's the things that you use here in the classroom. What this is taking is the cost of all of these resources, how much of these resources we use in the United States every year, and then dividing it by the population. And here we are. That's how many resources, approximately, each American takes in 1 year. It takes a lot of energy and a lot of resources to keep up our way of life here. And who do you think's find those resources? Geologists. Okay. So, this is the distribution of coal in the United States. Everywhere you see that is red, that's the bituminous coal. That's what most of the coal we use. Orange and kind of brown, that's the lignite and subbituminous. Okay, so there's a lot of it up here in the US, the mid-US. Anthracite is all black. Where do you see the anthracite? How much of it is there? Yeah, 1, 2, 3 places here in the US, not very much of it. Again, biggest reason why it is not a commercially used fuel source. You can buy anthracite. You can go to Tractor Supply and probably buy a bag of it. There's just not enough of it for it to fuel everything. So we don't. All right. Last thing I want to mention is how we get oil and natural gas. Okay, so this is part of what we call the carbon cycle, where carbon is continuously moved through our planet. Okay, so carbon is essential for things to be alive with. Okay, anything that's alive has carbon down to its molecular structure. Okay, that carbon usually is absorbed through things like the things that you eat, carbon dioxide in the atmosphere, etc. Something dies, like a plant dies, it either burns or it rots away, but either way, its carbon is released back into the atmosphere or down into the soil. If it goes into the atmosphere, it gets absorbed by rain, falls down through the rain, gets absorbed in the soil. But either way, you get this cycle of carbon through all of Earth's systems over and over and over. When it's part of life here on Earth, it's usually tied together with hydrogen and oxygen, making a hydrocarbon molecule. Okay? So here we have stuff, things living in the ocean hundreds of millions of years ago. Okay? Those things, they die. They fall to the bottom of the ocean. They get incorporated into the clays down there. All those clays that form in the calm water near the bottom of the ocean. That clay, now rich in hydrocarbon material, gets buried deeper and deeper and deeper. It gets hotter and hotter and more pressurized. We call this process cooking. When you take hydrocarbon material and you heat it, we literally, that's the term we use in the oil industry, is cooking. It's being cooked. Once it's cooked to a certain point, it goes from being in a solid state to being in a liquid state. And that's how you get oil, crude oil. Okay? That crude oil sits underground in that shale until the pressure increases to the point where it starts getting pushed one way or another. It's seeking zones of lower pressure. So it's going to move through the rock until it encounters a layer of rock that has enough holes, aka pore spaces, between its grains, usually a sandstone or something like that. It can migrate from the shale source rock into the sandstone, which we call the host rock. That's the rock that we will find it in when we drill down there with our straws and we pull it up. So the oil forms in the source rock, moves into a host rock, which is where we pull it from. That's how you do it conventionally. If you've ever heard the term conventional oil play and unconventional oil play, conventional is when we drill down into a layer of rock where it is being hosted because it's in the layers of rock, it's in the pore spaces of the rock, and we can pull it up. Those are becoming harder to find. But there's still a lot of oil in the original source rock. That's an unconventional play. When you go places where it's not easy to get the oil, why isn't it easy? There's no pore spaces in shale or mudstone. There is in sandstone, which is why it was easy to get it out of there. There's none in shale or mudstone where the oil came from, that source rock. So what do we have to do? We make our own pore spaces. We call it fracking. When you drill down into that layer of rock that has no pore spaces in it, and then you pump water down there, and you pump so much water, you pressurize it harder and harder and harder until you crack that layer of rock. And then you shove sand down there to prop those cracks open. Now that there are pore spaces for the oil to escape from, it floods up that hole that you drilled. That's how fracking works. You pressurize down hole so hard it cracks the rock, and then the oil can leave that rock and come up. Okay? So that's what fracking is. Okay? So either way, we get the oil up. Now, if my oil sits down there long enough, it gets overcooked. If it gets cooked too long, it becomes natural gas. It's hard for us to tell just using our instruments here at the surface if what we're looking at down there is oil or natural gas or water. And definitely the difference between oil and natural gas is harder to tell. So most of the time, we don't know until we drill down there to try it. If we drill down there and we find just a pocket of gas, no oil, we know we just got there a few million years too late. It overcooked. So our solid hydrocarbon content turns into crude oil. That crude oil, given enough time and more cooking, turns to natural gas. And that is your oil process there. Any questions about that? Have you guys ever heard that oil is made from dinosaurs? Sorry to burst your bubble, but no. I would venture to go so far as to say that no dinosaurs, or very, very few of them ever, were put in a situation where they could turn into oil. They decay at the surface way too quickly. This process requires organic material to get buried in environments where it does not decay, like the bottom of the ocean. Okay? Most of the oil, 99.9999% of all the oil, comes from algae or microscopic things living in the ocean, like those foraminiferans and diatoms and planktons and things like that. Okay? It is possible to get oil from coal beds as well. Coal oil, it's called. Not as common. So most of our oil does in fact come from the little things that lived in the ocean. Any questions? No? Okay. Well, that's your lecture. Let me give you a quick intro to your lab, and then we'll call it a day. I didn't push that. I wanted this. All right. Lab 3, sedimentary rocks. It's a very short PowerPoint. It's mostly just hitting the highlights of what we talked about in today's lecture. So I'm going to skip through some slides, just get to the stuff that we need to talk about in particular. Okay, so we talk about some of the more common ingredients here: quartz, calcite, clays, etc. Grain size, just a refresher on that sort of thing. The different textures you can get in non-clastic sedimentary rocks. Refresher on things like cross-bedding, graded bedding. We talked about all that today. Some of the more common rocks. That's pretty much your PowerPoint. That's really all that's there. Everything that you need to know for this lab, you just got in lecture. Okay? So there are 12 samples, and you're going to go through the same process that you have for the previous 2 labs, where there's a few questions at the front. Then you're going to find the properties, and you use those properties and compare them to the spreadsheet to find your right answer. Any questions about the lab? How many of you finished lab 1? Great. Is anyone ready for lab 3, or do you want to take today to finish lab 2? Okay, catch up on lab 2. That's always what I would prefer. I always prefer that you finish the previous lab before you start the next one, even if it makes you a little late. I will always understand, because the process and doing the process right is more important than sticking to a deadline. To an extent, remember, the only deadline I cannot extend is the end of the term. All work must be due by then. Okay, must be turned in by then. Okay. All right, well, and if any of my online students have questions, you can always leave me a question on GoReact or send me an email. Email is always preferred, but GoReact helps improve engagement. All right.